Math 1314, section IC1, spring 2022, Tyler Junior College, homework 9.1/9.2, inverse functions, exponential functions. Video 2, finding the inverse of a function. In the previous video, what did we do in the previous video? Well, let's take a look at it. Got it right here. In the previous video, we defined what an inverse function was. But we didn't really talk about how to find this inverse function. So in this video, we're going to talk about how to find this inverse function. Excuse me. All right, so let's recall a few things from the first video. Quite a few things here, so let's just focus on them one at a time. We'll throw some boxes around so you can see where I'm reading. Let's start by recalling that two functions, f of x and g of x, are inverses if the following statements are true. We have to have four things true in order to be inverse functions. Number one, the domain of g of x equals the range of f of x. In other words, the numbers that go into the g function have to be able to come out of the f function. Number two, the domain of f of x equals the range of g of x. So vice versa, the numbers that go into the f function have to be able to come out of the g function. Number three, f of g of x equals x for all x in the domain of g of x. Translation: for every number that you put into G, you should be able to do this. Excuse me. Let me turn off my email so that won't ding dong all throughout the video. In other words, f of g of x equals x, meaning that when you put a number into G and then the output goes into f, the output of that has to match what you started with, but your x has to first go into the g function, which is why this is true for all x in the domain of g of x. And thirdly, or fourthly, g of f of x equals x for all x in the domain of f of x. Same thing here. This composition, g of f of x, remember that composition in any composition, g of f of x means g of f of x. So whatever you're putting in for the fourth line has to first go into the f function, which is why it's true for all x in the domain of f of x. All right, so four things have to happen in order to be inverse functions. And I'll be honest, the domain and range, for the most part, we don't have to worry too terribly much about. I can construct examples where it is a big issue, but for now, let's just assume that the domains and the ranges are going to behave, and we focus more on the double composition. F of g of x is equal to x, and g of f of x is equal to x. Now, also recall that a function, f of x, has an inverse if and only if f of x is a one-to-one function. In other words, if f of a equals f of b, that implies that a equals b. Or in terms of outputs and inputs, if two numbers come out of the function the same, then they had to go into the function the same. This is equivalent to saying that if you put in two different numbers, you'll get out two different numbers. Now, there were ways to check visually whether or not a function was one-to-one. Sorry, my stuff's acting crazy here. This can be checked visually if the graph, that says if, I'm going to change it in a second, if the graph go. This can be checked visually. What is going on here? Sorry, folks, things are going all over the place. I'm not quite sure what's happening. Okay, that's what I get for trying to edit on the fly, but hey, I've seen worse things happen before. All right, so we can see if a function is one-to-one by checking visually if the graph of y equals f of x passes the horizontal line test, meaning that when you draw a horizontal line, you can only hit the graph once. That makes it a one-to-one function. Or if the graph of y equals f of x is strictly increasing or strictly decreasing, meaning from left to right, either the graph is always going up or the graph is always going down. It never fluctuates in a vertical direction, because if it does, then that curve causes the point where it would fail the horizontal line test. All right, but we didn't answer how to find an inverse function. For example, suppose f of x has an inverse function. I do want to remind you that the notation for the inverse of a function looks like this. Now, in the definition, they're called f of x and g of x. That's just to be two generic functions. But if you know one function has an inverse, then you can call its inverse the same letter with the little -1 in what looks like an exponent, but this specifically means the thing circled in red. I am the inverse of some other function whose name is f of x. So how can we find f inverse of x? For example, let's say we want to find the inverse of f of x equals 2x plus 5. It's worth mentioning briefly that this function does have an inverse because it is a one-to-one function, because it is a line. Specifically, it's a line whose slope is 2 and whose y-intercept is 5. So it would probably look a little something like that. But in terms of being an invertible function, it will pass the horizontal line test because any horizontal line that I shoot through it will only cross at one place. But let's assume that we already know it's going to have an inverse. How do we find this inverse function? Well, just for now, for the sake of cleanliness, when we do this, let's call this inverse function g of x. At the end, we'll stop and call it its proper name, which is f inverse of x. What do we know that this thing has to do? Well, we know the domains and ranges have to match the range in the domain of the original function, but we also know that the composition in both directions has to produce an x. In other words, 3 and 4. To be honest with you, these two things are the main driving force behind two functions being inverses. In other words, that they undo each other. When I do one function and follow it by the other, I get back the x that I started with. So we're going to focus on this property of being inverse functions to find the inverse of this. So how do we do that? Well, we're going to set up something and solve it. And from this, we're going to extract a process. We know that in order to be inverse functions, we have to have f of g of x is equal to x. Now we could also do it the other way around, g of f of x equals x, but I want to set this up so that the thing that we don't know is on the inside. In other words, f of g of x is equal to x. Now, how can we take advantage of this? Well, we don't know what g of x is, but we know what f of x is. And more specifically, we know what f of x does. F says, give me something, and I will do this to it. Specifically, I'll take the thing that you give me, put a 2 in front of it, and then add 5. Well, what is this f doing its thing to? This. So I may not know what g of x is, but I know what f is going to do to it. This particular function, this f of x, says, give me something, I'll double it, and then add 5. That's what f does. F says, give me, in this problem, f says, give me something, I'll double it, and I'll add 5 to it. The thing it's doing that to in this case is a function we don't know, g of x. This produces something called a functional equation. This is still equal to x, by the way. It's called a functional equation because it's an equation involving a function that we don't know. Now, we can solve this for g of x because remember, we want to know what g of x is equal to. And we can solve it the same way we solve for anything else. We can just get rid of everything attached to it. Specifically, we can start by subtracting 5 from both sides. That would cancel the 5s on the left and leave 2 times g of x is equal to, and on the right side of the equal signs, we have x minus 5, which we can't complete because we don't know what x equals. So all we can do is write x minus 5. Let's move this up here for a second. We have 2 times g of x is equal to x minus 5. And then, of course, to solve for g of x, we'll need to get rid of the 2. Since the 2 is multiplied, we'll divide both sides by 2. That will cancel the 2. And we have g of x equals x minus 5 over 2. Now, is this truly the inverse function? Well, we could check the domains and ranges. This is a line. It's not in slope-intercept form, but if I split it into 2 fractions, it would be 1/2 x minus 5 halves. So it's a line whose slope is 1/2 and whose y-intercept is -5/2. More importantly, it's a line and it's not horizontal because that would fail the horizontal line test. And it's not vertical either because that would have an undefined slope. This has a slope of 1/2. So this is a line that will go from bottom to top and from left to right forever, just like the original function is a line that goes bottom to top, left to right forever. So the domain of one matches the range of the other because all the domains and ranges for both functions are all real numbers. So it satisfies the domain and range stuff. Now, does it satisfy the double composition? In other words, does it satisfy criteria 3 and 4? It does, and I invite you to try to verify that. But we now have, and we'll just leave the function in this form, we now have our inverse function. But more importantly, we've kind of developed a technique that got us there. Let's pick it up from here. If you think about it, all we did was solve for this guy. Yeah, we called it g of x, but the motions that we did were the same if we were solving for x in the original function. So let's see if we can take this process and turn it into something a little bit more general that will always get the job done. In other words, how to find the inverse of f of x. Now, this, of course, is assuming f of x has an inverse, because not all functions have inverses. For example, f of x equals the absolute value of x doesn't have an inverse. The reason is, if I told you that I took an absolute value of something and got 4, you don't know what I took the absolute value of. Did I take the absolute value of 4? Did I take the absolute value of -4? It's impossible to know. So my inverse function can't undo what the absolute value function did because it doesn't know what original number I started with. So assuming that the function has an inverse, here's how you find it. All right, step 1. Rewrite let's change that verb. Let's say change f of x to, well, I want to change it to something that it represents, and it always represents a y coordinate, so we're going to change that to y. Okay. Number 2, we're going to, well, let's think about what we did here. When we were at this line, we had embedded g of x inside the f function. But isn't the output of a function typically called the y coordinate? Doesn't have to be, but it typically is. So what can we think of instead of saying g of x? Well, we can just think of it as a y. But if we stick the y in there, then we can't have the y on the other side. In other words, if we took this function f of x equals 2x plus 5, and said, well, that's just another way of saying y equals 2x plus 5. And compare that line with the other one currently in the blue box. In other words, if we compare these two things, then positionally, the thing that is inside the function is g of x, and over here it's just an x. In order for the left blue box to look more like the right blue box structurally, we would want the y to be there, not the x. Plus, take a look at what's on the other side of the equal signs. This is just a y, this is just an x. Well, keep it in mind that something like g of x is just a fancy name for y. So pretend this thing flashing is just the letter y. Then the two equations in the two blue boxes on the left and in the center are identical. The only difference is the x and the y switch places. So we're going to use that as a motivation for our second step to say that we're going to switch the x and the y. It's going to be step 2. Step 2, switch x and y. And what this does is it takes the y and it embeds it inside of the function that we're given. And once we did that, basically what we did in the blue box in the middle is, if you pretend the g of x is a y for a second, if you pretend this g of x is a y for a second, we basically just solve for that y. So we're going to embed the y inside the given function by switching the x's and the y's, and then we're going to solve for y. The result is the inverse function f inverse of x. I'll put the little -1 there in just a second. I've got to, if I want to put it there and not draw it there, I actually have to set up a text box of a smaller font size and then move that text box here. There we go. All right, so how to find the inverse of f of x, assuming f of x has an inverse. And you won't be asked to find an inverse if it doesn't have one. So if you ask to find one, trust me, it will. Number 1, change f of x to y. Number 2, switch x and y. Number 3, solve for y. So basically, we introduce y into the function notation, switch the x and y to bury the y inside the function, then we dig it out by solving. And in the process of doing that, we create the inverse function. So let's take a look at a little bit more involved example than the previous one, now that we have a process to follow. Example, find the inverse of f of x equals 3x minus 10 over 29. Now, I typed this horizontally because I can't type vertical fractions. Personally, if I were writing it, I would have written it like this. A big fraction with 3x minus 10 on top and 29 on the bottom. All right, if we're going to find the inverse, then we're going to follow a 3-step process back here. The first of which is to literally change f of x to the letter y. So the first thing we're going to do is write y equals instead of f of x equals. That was step 1. And step 2 is to switch x and y. So now we're going to pull the switch. Switch, every y becomes an x, every x becomes a y. And now that we've buried the y inside, excuse me, inside of our given function, now we're going to solve for y, dig it out of the function, and in the process, on the other side of the equal sign, we'll start building the inverse function. So our next move is to solve for y. Now, it may look tricky to solve this for y, but it's actually not that bad, because think about what happens when you put a number in for the y. If you follow the order of operations, the first thing you would do is you would multiply by 3, then you would subtract 10, then you would divide by 29. So we just got to reverse that process. If I want to solve for the y, the first thing I have to do is undo the divide by, it was 29, wasn't it? Yes. Undo the divide by 29. So we're going to start by multiplying both sides of this equation by 29. Times 29 and divided by 29 are inverse operations, if you will, in the sense that they cancel, and that will leave on the left 29x and on the right 3y minus 10. And now I'm going to get rid of the minus 10 by adding 10 to both sides. Or rather trying to add 10 to both sides. I said try, because even though on the right side the 10s cancel, what am I going to do on the left side? On the left side, I have 29x plus 10. If your brain's trying to say 39, shut that down, because those are not like terms. The 29 is counting how many x's I have, the 10 is not. The best I can do on the left side is to write 29x plus 10. If you're trying to add unlike terms, you can't. Just leave them alone. On the right side, we still have 3y. And then, of course, to finish solving for y, to unmultiply by the 3, we'll divide both sides by 3, or rather try to divide both sides by 3. The result on the right side is the 3's cancel. The result on the left side is nothing. All I do is set up a bigger mess. But that's okay, because we were trying to set up a function on the other side. 29x plus 10 all over 3. That can't be simplified. I can't combine anything on the top. Nothing will reduce, because the only number I could reduce by on the bottom is 3, and nothing on the top is reducible by 3. So we're done. That means that our answer is the inverse function is a big fraction with 29x plus 10 on the top and 3 on the bottom. There's our inverse function. We could verify that this has the same domain as the original function's range and vice versa. And we could do the composition in both directions, but I promise you it will get the job done. Now, I know some people are going to start thinking, wait a second, these are the same numbers that I had in the original problem. All they did is move around some, and you might start speculating, can I just move this here and change this to that? There is something to do to that. I invite you to investigate it further, but you still need to be familiar with the process because sometimes it won't always be obvious how to get the inverse. I want to do one more example that is going to be a little bit more complicated. For example, find the inverse of f of x equals 6 over x minus 3. Again, when I type my fractions, I have to type them horizontally. I would rather write them vertically. 6 over x minus 3. Now, does this even have an inverse? Actually, it does. Without rehashing all of the homework 8.1 and 8.2 content, this being a rational function would have a vertical asymptote at x equals 3 because it makes the denominator undefined. Well, it makes the denominator 0, but not the numerator. As a horizontal asymptote, it would have a horizontal asymptote at y equals 0. The degree of the denominator is greater than the degree of the numerator. The y-intercept is what I would get when I put in x equals 0. That would give me 6 over negative 3, which is negative 2. I don't know anything about what's on the right side of x equals 3. So if I went over to x equals 4 and put in 4, I would get 6 divided by 1, which is 6. So way up here, I'll have a point. And if you got more dots, you would see that your graph looks something like this. And the graph does pass the horizontal line test. Again, it's not necessary to verify that your function is 1-to-1 or that the graph passes the horizontal line test. If you're just point blank asked, go find the inverse. The implication is because the inverse exists, so there's no need to verify it. But I just wanted to show you that we can fall back on prior information to move stuff forward in what's going on here. To move stuff forward as we move forward. All right, so let's find the inverse by doing our 3-step process. Number 1 is we need to change this to y equals. That's an easy move. And then step 2 is to switch. So everywhere there's a y, we put an x. Everywhere there's an x, we put a y. It's the third step that's going to cause trouble sometimes, where we have to solve for y. Well, let's talk about how we would take the equation x equals 6 over y minus 3 and solve that for y. Well, the biggest obstacle right now is we want this to say y equals, but the y is currently in the bottom of a fraction. We're not going to make it say y equals as long as the y is down there. So we need to get the y out of the bottom of the fraction. The easiest way to do that is to kill the fraction by multiplying both sides by the denominator y minus 3. The left side and the right side. That will cancel the y minus 3's on the right, leaving just the 6. And on the left side, we have y minus 3 all times x. All right, so we're a little bit closer to our goal of y equals, but we're not there yet. So what is currently preventing us from having the y by itself in this line? There's more than one correct answer to that. Number 1 is the minus 3, which we have to take care of at some point. And number 2, there is an x sitting outside the parentheses, keeping the parentheses there. So at this stage, we need to fix one of two things. We either need to get rid of the parentheses or fix the minus 3. Well, we really can't fix the minus 3 because it's currently trapped inside of parentheses. So what can we do to fix that? Well, what's the standard way of getting rid of parentheses? The answer is to do the multiplication problem that they're sitting on. In this case, that would mean distributing the x. So I'm going to distribute the x to get x times y minus 3x is equal to 6. That eliminates the parentheses and gives us access to its contents. And now we can proceed to start solving for solving for y. If we're going to get the y by itself, now we've got another issue. We just created one problem by fixing another. We fixed the parentheses and we created the problem of sticking an x in front of the y. And we've got a minus 3x after it. So we got to get rid of something that's multiplied on the y, the x, and get rid of the minus 3x. In standard linear equation solving protocol, we usually get rid of the stuff that's added and subtracted first. So let's add 3x to both sides to get us closer to our goal of getting the x by itself. That will cancel the minus 3x on the left and leave just the xy. But on the right side, we have an addition problem that we can't complete. We can't complete 6 plus 3x because they're not like terms. So all I can do is write 6 plus 3x. It wouldn't be wrong to write 3x plus 6 either. Let's continue this on the next page because I don't want to try to squeeze the rest of this problem in that little bitty space there. All right, so we're in the midst of step 3, continued. And we are trying to solve for y. And we currently have xy equals 6 plus 3x. What was the only thing preventing the y from being by itself? The x multiplied in front of it. And how do we get rid of something that's multiplied? We divide. Let's divide both sides by x because that is the one thing preventing us from our goal of getting the y by itself. That will cancel the x's on the left. Let me change colors when I cross these out. We'll use blue. That will cross out the x's on the left, leaving just the y. Now, what happens on the right side? Well, actually, one of two things. We could leave it as 6 plus 3x over x. There's nothing wrong with that. But let me tell you what not to do. Don't cancel these x's. Why? Because to be cancelable in a fraction, you have to be part of a multiplication problem. Now, you might argue that this x is part of a multiplication problem. It's part of 3 times x. But that multiplication problem is part of this addition problem. You cannot cancel parts of addition problems in a fraction. You can only cancel parts of multiplication problems. So we can't cancel the x as is. But there is a trick here, and we've seen it before, where you take this fraction and unadd it by writing it as the sum of 2 fractions, each with the same common denominator, and then splitting the terms of the numerators into their own fractions. And what that does is it sets up a fraction here that I can cancel in because there's no longer any addition in the numerator. So if we split it like that, then these x's would cancel, and that would boil it down to 6 over x plus 3. So which answer is correct? Both of them. 6 plus 3x all over x or 6 over x plus 3. Either one would get the job done. Most people would probably go for the first answer because there's more work to get to the second answer. This means that our inverse function, f inverse of x, is 6 plus 3x over x, or if you wanted to split it and clean it up, 6 over x plus 3. Either one would be correct. But again, I think most people would probably settle for the first one because it requires less work.